Hello everyone. So this is our video for Project 4, Among Us. And the first thing I want to mention is that there are three parts to this project. A, B, C, which is MST, Fast TSP, and Optimal TSP. TSP is the Traveling Salesperson problem. Once you've seen the MST lecture, you've got everything you need for Part A. When you've seen the TSP lecture, the backtracking, branch and bound, and TSP, you'll have everything you need for Part C. Part B is a lot like Part C, but you're going to have to do a little bit of research on your own. So if you're watching this video before the backtracking, branch and bound, TSP lecture, not all of this is going to make sense when we get to Part C. Now, you do want to do them in order, A, B, C. For all of the parts, make sure that you watch for the autograder output that says hint. If it says hint, read it. It's got some good information in there. The other thing about this project, true about all the parts of this project, is that unlike other projects, your output can be different from ours and still be correct. And every part of the project, A, B, and C, is judged by a different program on the autograder that we call the judge. So let's just do a simple example of MST. Suppose I've got 4 vertices. All right, I've got A, B, C, and D. And let's pretend that those are all equidistant, that the distance here is 1, 1, 1, and 1. And let's assume that I don't connect. There is no connection from A to C or B to D, just to make things simpler. An MST of this might list the vertices A goes to B, goes to C, goes to D. That's an MST. This is an MST, this is an MST, and this is an MST. So there are 4 different MSTs that you could produce. They're all equivalent. They are all minimal. They all have a cost of 3. So not only are there 4 solutions that look different, in your output you could list the vertices in a different order, and the judge will still say you're right. The time the judge would say you're wrong is if you did something like this. That one, it would say, no, you're wrong. You've got 3 edges, but the length is not 3. The length is like 3.414. So you can get different output from us and still be correct, which can sometimes, for larger graphs, can make it a little bit harder for you to tell if you've got the right output. So the big thing to look for is the first line of output is going to be the total weight of the graph, or the total weight of edges used. So look at that number. If that number is wrong, then something's seriously wrong. If that's right and the other stuff is wrong, it might still be valid. And there's a tool that's listed in the appendix that lists it's a particular link to AutoGrader 2. It's called a visualization tool, and it will allow you to load up an input file and an output file and tell us what it represents, whether it's a TSP or a MST, and it will draw it out for you in the browser. So you could, for instance, load up like these 2 solutions, simple example, load up these 2 in 2 different browser tabs and plot them and look at them and see how they look. Okay, now let's talk about some more about Part A specifically. So the first thing we need to know about Part A is, hey, I've got to pick an algorithm. I've got Prims, I've got Kruskal. Is this a dense graph? Because if it's a dense graph, we want to use Prim, and if it's a sparse graph, we want to use Kruskal. So let's assume that all of the starting locations are in the lab. So if I had all of the starting locations in the lab, and there are n of them, I would have approximately n squared over 2 possible edges. Now, if you haven't gotten to this part of the spec yet, there is the lower left quadrant is the lab. The edge between the lower left quadrant and the rest of it is referred to as the decontamination area. And then there are the outer rooms. So you cannot travel directly from an outer room to a room in the lab. You would have to go through a decontamination room before you could go to the lab. So for instance, if we call these vertices like A, B, C, D, E, and F, you cannot go directly from C to D. Oops, we forgot to give the decontamination a letter G. You cannot go directly from C to D, but you could go from C to G and from G to D. Those would be G to D. Those would be valid. So this line is disallowed, but that's valid and that's valid. So you can go C to G, G to D. You can't go from A to D. You would have to go from A to G to get to D, or A to B, or A to C. So we can't cross the decontamination area without stepping on a decontamination room. So if everything was in the lab, it would be completely connected. It would be approximately n squared over 2 edges exist. See, we're not going to list edges for you. We're just going to list vertices and tell you where they are. Now, so if they were all in the lab, it would be approximately n squared over 2. If they were all in the outer area, it would be approximately n squared over 2. If there was, let's say, almost all lab and just one decontamination and one outer area, it would be almost completely connected. So the worst case would be if we had basically approximately half of them are in the lab, approximately a half of them are in the outer area, and there's one decontamination. So then we would have, in the lab section, there would be n over 2 squared over 2 edges. In the outer area, there would be n over 2 squared over 2. If we add these up, this is basically n squared over 8 plus n squared over 8 is equal to n squared over 4. N squared over 4 is still a pretty dense graph. So in part A, it's always dense. Since it's always dense, we want to use Prim. We want to use nested loop version of Prim. Now, about the input. The input file will look the same no matter whether you're doing part A, B, or C, which says I should probably have a standard way to read input and a standard way to store the input. I just want to have, well, I have to have XY coordinates. We promise the XY coordinates will always be integers. So I could have a struct containing 2 integers, the X and Y. Now, don't use pairs. You're going to be tempted, you're going to want to use pairs, you're going to go, oh, there's 2 things, I'll use a pair. Don't use pairs. Because then instead of saying dot x and dot y, you have to type dot first and dot second, which is harder to read. And if you decide to add, say, one other thing, like I might say, it would be really nice if I had an x and a y as integers and a classification. What type of room is this? Is this room in the lab? Is it decontamination? Is it in the outer area? Which one is it? I could use an enum for that. I could use an enum class for that, or I could use a character, LDO for lab, decontamination, outer area. Either one works. So then we could always store our input that way. Even if we're doing B or C, we could still have that little extra enum. You won't go over memory. Now, The other thing when we're talking part A is don't make a structure containing X, Y, type of room, and distance, is it true or false, and who's my connected predecessor vertex. Don't put it all in one data structure. Have a vector of what you read in, and then if you need prim info, you could have a vector of the K, P, and D. Is it known what's the best distance, who's its predecessor? And remember, when you make that structure, always go largest to smallest or smallest to largest. Don't go in the order that, oh, I got to do them in the same order they're listed in the MST slides. I've got to do the bool, then the double, then the integer. That wastes memory. That will go over memory. So we want a structure for what we read in, and we'd have a vector of those structures. When we're doing stuff that's related to MST, we can have a different vector of our prim info. Now, the one way to make this project easier is Prim shouldn't know anything about lab, decontamination, or outer area. That makes your code in part A too complex. And people will start saying like, ooh, I'll just make an MST of all of the lab, and then I'll make an MST of all of the outer, and then I'll just find one way to connect them. That's not the right way to do it. Because what if we had two decontamination locations? They would have to connect to each other. Or maybe in this one should connect to that decontamination, that one should connect to that decontamination. If you try to do an MST of the outer area, you would ignore that shorter edge and pick this longer edge. So don't do it. So how do we make it simple, but still abide by the rules? So let me just actually clean this diagram up a little bit, and we'll get less points here. All right, so I've got points here, A, B, C, and D. Okay, you are Prim, I am your helper. You say A and B, what's the distance? I say 3.8, okay? All right, so the distance from A to B is 3.8. And you say to me, what's the distance from B to C? I say, distance from B to C, that's 1.3. Okay, you use 1.3. You ask me, what's the distance from A to D? Well, I, the helper, I know that A is in the outer area and D is in the lab. You can't connect those. But I've got to return something to you. I've got to return a double, right? This is where we get, it would be really useful for me to return infinity. So what we do is we pound include limits, and then we use numeric underscore limits, angle brackets double, colon, infinity, parentheses. So numeric limits double of infinity is what I would return to tell you you can't do that. Back in Prims, you don't even check if it's infinity. You just take the double that I gave you and compare it and say, is this better than what I had before? No, I don't use it. So that makes your Prims much, much easier. Simple thing you have to be careful of in part A. And really, not just part A, it could be every part. I know it happens in part A, but it could be any part. When you're calculating Euclidean distance, you've got to be careful because of integer overflow. Suppose I had two coordinates, and one of them was at x equals negative 25,000, and I have another one where x is equal to, let's call it x1, x2 is equal to positive 25,000. and I start calculating the distance between the x portion of the distance between these 2 points. 25,000 minus negative 25,000 is 50,000. 50,000 squared is negative 500 million because of integer overflow. So you can subtract as integers, but before you start squaring, you want to go to doubles. Don't use the square function. Do not use the pow function. There's no square function. Don't use the pow function. Just multiply the difference in x times the difference in x, but make sure that the difference in x is a double, not an integer. So it's safe to do the subtraction, but not the multiplication. Okay, now when we get to parts B and C, one thing, hint for you here, on parts B and C, besides your vector of the coordinates, your x and y and stuff, and maybe your enum, keep a vector of indices. That represents your path through the different rooms. Why indices? Well, one reason is when you're done, you must print the indices. And if you go start adding to every vertex, adding another integer, then you might go over memory. So you got to be careful about adding too much to that. So instead of having one vector, which is the coordinates and the order that they're in, what you want to do is just have your vector of inputs and a separate vector of indices. And so in part B and C, you're going to manipulate the order of those vertices, the order of the indices into the vertex vector. Now for part B, the idea of part B is that, hey, we'd like to do a traveling salesperson problem, but we've got too many vertices. We do not want to wait, 57,000 years for 25,000 vertices to finish. But what we'd like to do in part B is we'd like to get an estimate. I don't want it to be insanely large. I don't want it to be a terrible solution, but I want a good solution in a reasonable amount of time. So when you get to part B, which is called fast TSP, what you want to do is go onto the internet, do a search for TSP heuristics. So go do a search for that. There's lots of different heuristics. One thing you want to make sure is you want to stick to things that are O of n squared. If it's longer than O of n squared, like n squared log n, it's going to take too long because we're talking big n's here, like 25, 40, 50,000 vertices. All of these heuristics are greedy. They're just different in the way that they are greedy. So one of the simplest ways that you're going to see is called nearest neighbor. So what you do is you just pick a starting vertex. Oh wait, you don't pick the starting vertex. Spec says you've always got to start at vertex 0. So I start at vertex 0, wherever it is. I don't care about x, y, just the order that you read it in is its name of that vertex is the index that you read it into. So vertex 0 is my starting point. I find the first vertex to 0. I don't care who it is, whoever's closest, that's your next one in your path. And then that one is now the end of your path. We find the closest vertex to that one, and we go there. And then we find the closest vertex to that one, and we go there. And then we find the closest vertex to that one, and we go there. And then we find the closest vertex to that one, and we go there. And then, let's say this was the last vertex. Now I've got to get back to home. Got to get back to my starting point. But that is where we see the flaw in the greedy nearest neighbor heuristic, is my path crossed itself. A path that didn't cross itself would be a shorter path. So if you do greedy nearest neighbor, you've got two choices. Well, three choices. Don't do greedy nearest neighbor, pick a better heuristic. Or you could do greedy nearest neighbor followed by something called 2-opt. And the slides There's a set of slides called the tutorial slides, has more information than the video and some examples. The tutorial slides show you how to-opt works. Or you can just go pick another heuristic. Some of the heuristics require you to have a data structure that you keep track of things. Some, like the greedy nearest neighbor, you just have to keep track of really who you've picked and who you haven't picked. Okay, when we get to part C, so part C, which is called opt-TSP, meaning optimal, when we get to opt-TSP, we've got a severely limited number of vertices. Like if I've got 5 vertices, I can do part A, part B, part C. But if I've got 5,000 vertices, I can't do part C. So I can guarantee you part C is never going to have more than like 40 vertices. Now, this actually tells us something else about our data structures. You might think, hey, when I had that back in part A, we talked about having a helper to calculate the distance between 2 vertices. Why don't I have a distance matrix? Well, I've got a problem. In part A and part B, I might have 50,000 vertices. 50,000 vertices, a distance matrix would have 50,000 times 50,000, that's 2.5 billion locations in the 2D vector. Each one of those would be an 8-byte double, which means I need 20 gigabytes of memory for my distance matrix, and you can't afford that. One, the autograder won't let you grab more than 4 gig, and even if it was moderately large where you could grab a 2 gigabyte distance matrix, you'd go so far over memory you'd lose all the points. So A and B, you cannot have a distance matrix. In part C, if you want one, you can have one because I've got 40 vertices. 40 times 40, 1600. 1600 times 8 bytes, that's like 11 kilobytes. That's not bad, I can do that. So if you want to, you can do part C with a distance matrix. It will make it a little bit faster. Now, when we're dealing with part C, next tip is in the backtracking and branch and bound slides, we're going to give you a function. We're going to show you a function called Gen Perms. Now, the Gen Perms that we're going to show you is a little bit different from the one that we showed you earlier in the semester. And I want to I'm just pulling it up on my computer here. Okay, so you've got the right version if Gen Perms has a vector of type T, ampersand path, and then size T, perm length. So if you've got the earlier version from like back, I don't remember which lecture it was, I don't want to know because you don't want that version. But on Canvas, we put a file called genperms.txt that's got the identifier, the project identifier in there for easy copy paste, and it's got the Gen Perms function, this version that you want to use. Now, one of the things about this Gen Perms is that it doesn't have everything. Like, if this was a function, where is my vector of xy locations? Remember, I said we want this to be a vector of like indices, right? These could be like uint32t's or unsigned ints. I want these to be indices. If this is my path, my indices, where is my actual vertices, x and y locations? Where's my vector of those? Where is my best path? Where is my best distance I've ever seen? Where's my distance matrix? Where's all this stuff? The answer is, let's make a class. If we make a class and we make this a member function of, let's say, my part C class, if this is a member function, instead of adding parameters, I can get rid of parameters. Now, why? Why would I not want to add parameters? Because this function down here, it's going to make a call to Gen Perms, and then it's going to do some other stuff. So it's going to have a recursive call that is not tail recursive, which means every recursive call has got to go on the call stack. The more parameters you add, the more things that have to get pushed onto that new stack frame. Also, this Gen Perms function is O of V factorial. Do you want to push 7 things onto the call stack V factorial times, or would you like to push less? I'd like to push less. It would be faster. So we make this a member function. What our goal is now is to make as much as we can member variables. In fact, this path, hey, let's make this a member variable, and then we've only got one parameter, the current permutation length. It's possible to get rid of that and make it a member variable, but it takes a little more changes to the code than we want to talk about. So we want to make this a member function. We want to make a class to hold all the member variables. The path, the vector of vertices, our XY locations, or our room locations, we could call it, our best path we've ever seen, the best distance we've ever seen, maybe our current running total for our current distance, our distance matrix, all that stuff becomes member variables. Now, do you have to do a class? No. You could make global variables. And then when you go into a job interview and you pull out global variables in a coding problem, then I don't know about other coding interviewers, but me, I would say, we've seen enough. I've seen that you use global variables. I don't need the interview to go any further. Global variables are a crutch. They can solve a problem quickly, but they are a nightmare in a large program. So don't do that. Make it a member function, a bunch of member variables for everything you need. Okay, where was I? Okay, so make a class. Got that. So, and the running total. There's something important here about the running total. As you go through Gen Perms, you have to understand what Gen Perms is doing. And there's some calls in here. There's right before the call to Gen Perms, there's a swap. And right after the call to Gen Perms, there's another swap. And one of the things that you call Gen Perms with is you call it with perm length plus 1. So what you're basically doing is every time you make a call to Gen Perms, you're saying, let's try out a new vertex, adding it to the path. So I started out with like vertex, say 0. Then I tried adding vertex 1 to it. And then when I made another recursive call, I said, hey, let's try adding vertex 2 to this. Let's try adding vertex 2 to the path. So when I was starting out, when vertex 0 is in the path, my perm length, let's say just PL is equal to 1. There is one thing in the path. And then in the next recursive call, perm length is equal to 2 because there are 2 things in the path. The path vector never changes its size. If you read in 20 vertices, the path dot size will always be 20. But perm length, what it's telling you is how much of that is fixed and how much has yet to be decided in future recursive calls. Now, let's say we don't keep a running total. And by running total, I mean like, hey, there was like 5.7 here, and I added 3.4 in that one. I would have a running total of 9.1. Now, let's say you don't do that running total. You're going to try all the permutations. You're going to say, hey, let's try things that start out 0. Let's try things that start out 0, 1. Let's try things that start out 0, 1, 2. Let's try things that start out 0, 1, 2, 3. And if you don't keep a running total, you're going to sum up the things you just summed up. You're going to sum up 0 to 1, then you're going to sum up 0 to 1 plus 1 to 2, then you're going to sum up 0 to 1, 1 to 2, 2 to 3. then you'll sum up 0 to 1, 1 to 2, 2 to 3, 3 to 4. If instead you had a running total before each recursive call, we could add, I could say like my current length plus equals the cost of this new edge. And then right after the call to Gen Perms, I didn't quite leave myself enough room there, we could say current length minus equals the cost of that new edge. The swap statements here are what make the choice of which vertex am I trying out. I try 0, 1, 2, and then at some point later, I try 0, 1, 3. And at some point later, I try 0, 1, 4. So that's what the swap is doing. So if we add code to keep a running total, we do it between the swap and the recursive call, between the recursive call and the other swap. If you do that, if you keep a running total, when you get to the base case, you're going to be missing an edge. Because I went from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and then I ran out of vertices. Let's say there was only 5 vertices in this example. When I get to my base case, which is when perm length is equal to path.size, I've got 4 edges. But a real cycle would have 5 edges. When you get to the base case, if you keep a running total, when you get to the base case, you've got to say, hey, I've got to add in that edge from the last thing in the path back to vertex 0 to make sure that I close the cycle and get the correct total length. And then we do the base case stuff. Now, when you call Gen Perms, the path must contain all of the vertices. Well, not really all the vertices, the index of all the vertices. Also, remember, for all of these, for part B and C, you must start at vertex 0. That's not a requirement. It's not arbitrary. It's made to keep you from doing too much work. Because, let's say I just had 3 vertices. If I went from 0 to 1 to 2 and back to 0, 0 to 1 to 2 to 0, that's the same length and the same path as going 1 to 2 to 0 and back to 1. That's the same path as going 2 to 0 to 1 and back to 2. So I don't want to duplicate that effort. Now, there is a duplicate effort. I could go from 0 to 2 to 1 to 0. There's no easy way to stop that from happening. But there's an easy way to stop this from happening. The very first time you call Gen Perms, you call it with 1. You say the perm length is 1, meaning I have selected one vertex that must not move. The other n minus 1, you can permute those however you want, but you can never move this one. And then in other recursive calls, you say, hey, the perm length is 2. 2 vertices are fixed. In future recursive calls, you can permute the other ones, but don't change those first 2. And then as recursion unrolls, then you're allowed, when you get back to where perm length is 1, you're allowed to choose a different one for this. You say 0 is fixed. Now I can change this one. I make a recursive call. These 2 are fixed. Permute the others. So you want to make sure your very first call to Gen Perms is Gen Perms of 1 so that vertex 0 never moves. It's always the first vertex. Now, part of the reason to do this in order A, B, C is that that's the easiest. Second of all is that part C is probably going to want to use both parts A and B. We'll talk in lecture about why this is true. But here's the thing that's important in this tutorial is lots of students say, I've got a perfectly working part A. I changed it a little bit so that part C could call it, wait, why did I have to change it? Because in part B and part C, you don't care about lab and decontamination and outer. In part B and C, the graph is completely connected. So, if you just call part A and part A worries about decontamination rooms, then you would get the wrong answer. So people tell me, oh, I just copied part A, I used a different helper that calculates the distance and ignores decontamination, it's got to work. But it does, I get the wrong output, but it can't be my part A because I got all the pints for part A. Actually, that's where most students get part C wrong, is you have a perfectly working part A, your modifications were fine, but what's failing is your handoff from part C to part A. And here's where the handoff comes. The reason part C calls part A is that part C, Gen Perms, is going to fix some vertices. And then it's going to ask part A, does this look like a good start? So let's do an example. I have some vertices. And I start out 0, 1, 2, 3, 4, 5, etc. All right, so I go from 0 to 1 to 2 to 3, and now visually this is looking bad. But how do we get a program to tell us this doesn't look that good? All right, now let's say this distance is always 1. So these distances between vertical spacing is always 1, and so this is 1 over here, and this is 10. Okay. So let's say I told you my best so far is a distance of 60. All right, well, what have we got for a running total? So for whatever reason, the best solution I ever found had a distance of 60. Now we're starting out, we're in part C, and we're doing our thing with Gen Perms, and we want to know, should I keep going? So the TSP lecture is going to have information about this. But we call part B, and we ask part B, give me an estimate of the remaining cost. Not including vertices 0, 1, 2, 3, give me an estimate of these 6 vertices. And maybe maybe the numbers don't match exactly like I said. Maybe the vertex numbers are very different. Maybe I'm at the point where I'm trying 0, 7, 3, 8, and I have to take the MST of 4, 6, 2, 5, 1, 4, 6, 2, 5, 1, and 9. Now, a failed handoff from part C to part A would say, well, I've got to calculate the MST of 6 vertices. I'll calculate the MST of vertices 0, 1, 2, 3, 4, 5. Oh, that's not good. Well, you say, well, there's 4 of them are fixed. 6 of them can be changed, and you call part A, and part A gives you the MST of vertices 4, 5, 6, 7, 8, and 9. I don't want the MST of vertices 4, 5, 6, 7, 8, and 9. I want the MST of vertices 4, 2, 1, 6, 5, and 9. The order doesn't matter, but it can't be 4, 5, 6, 7, 8, 9. So this is where people fail the handoff from part C to part A, is doing the MST of the wrong vertices. Other things that you could fail is you could say, hey, because I know I'm going to call part A over and over, I'm going to have part A hang on to its Prims table. I'm never going to clear it out. I'm never going to get rid of it and recreate it. That would take too long. I'm going to keep my Prims table from call to call. That's not right. When part A finishes, there are going to be things that are true, vertices that are true, and vertices that are false. And there's going to be distances that I know are 2.3. But when I come in again, I've got to mark all of them as false. Or maybe I would mark these as true and mark these as false. and mark these as all a distance of infinity because I don't know them. So that's another way to fail the handoff to part A, is not to reset your prims table before calling part A. So there's lots of ways to get this wrong. If you start getting part C is getting wrong answers, there is some help in the README document that's in the sample files. There's a README document that's got some tips in there and how to use our sample files to get some better feedback. There's also some things that you can do. So in part C, if you're getting wrong answers, so there could be two ways you could go wrong in part C. So one way is you're getting right answers, but your time is just insane. You're losing all the points because it takes you 10 seconds to get a right answer when it should be 0.03. So if you are getting way too long on time, your problem is you are not pruning enough. You are not pruning out bad choices quickly enough, and you are exploring branches that the MST should have said, no, that doesn't look good. If you're getting wrong answers very, very quickly, what it means is you're pruning too much. You are pruning away the best solution. You're saying, hey, 0786 does not look like a good beginning. You shouldn't go down that path. 0786 looks terrible. So what you can do is, if you're getting part C either wrong or over time, what you can do is add some debugging output. You could also have both. You could have this test case, I get it wrong very quickly, and this test case, I get it right, but it takes forever. That tells me that you're both under pruning and over pruning. And if you fail that handoff to part A, depending on how you fail the handoff, you could be doing either one. You could be over pruning or under pruning. So what you can do if you're getting part C going badly, either taking way too long or quick wrong answers, is we're going to add some debugging output. Sorry, I've got a Maine Coon who's attacking a bag. In her defense, it probably did try to kill her, but you can't trust paper bags. Anyway, what we want to do is we want to add in our debugging output, we want to add the perm length, because that would be useful to know. I want to know the current path length. And by this, I mean the double. Like our, 5.7 plus 3.4, or whatever I did in my example. So that would be my running total. This is my running total. I would want my MST estimate from part A, and I would want, pretend this is all one line, I would want my connecting arms. Now, if you look at the TSP slides, basically the current path length, this would be the black lines. The MST estimate, that would be the gray lines in the lecture slides, and the connecting arms, these would be the two blue lines. So print all of these all on one line. Better yet, see out these using set width. Set width, make sure everything you say, hey, let's print this double in a width of 10. That'll make sure that every line lines up. Whether it's 1.23 or 128.47, the columns will all line up. This is going to produce a lot of output. It's going to go flying by. What you want to look for is a trend that doesn't look right. But you could see things that go wrong, like, what if my MST estimate was infinity? But that can't be right. What if my MST cost was 0? That's probably not right. What if my every call, the MST cost always goes down? That can't be right. Because what we should see is that as perm length goes up, this thing, so as perm length goes up, this thing should tend to go up, this thing should tend to go down, and these things should tend to do both. The connecting arms can go up, down, up, down. I've seen students, they tell me, I've been debugging for 4 days, I don't know what's going wrong. I say, do this output. 5 minutes later, they tell me, oh, one of my connecting arms is always length 0. There you go. So put this stuff in there, print it out, and look at what's going wrong. There's another thing you can do. When you identify a place that something went wrong, how do you know where something went wrong? Okay, for this example up here, I would say, and you can look at, like, what's the correct output for this? We'll generate it for you if you give us the test file. But correct output for this, if we start at 0, would be either 0, 3, 4, 2, 1, etc., or it'd go the other way around. It'd be 0, 7, 8, 6, 5, whatever. Okay? So if you never get that, then what you've got to do, look at this output that you're getting. You see this all, and maybe you print. Maybe we could add some other stuff to this. Maybe we could print out which vertices are in the MST. Like at the very end of this will vary in length, we could print out the indices in the MST. So if I print which indices are in the MST, I could see the point at which something went wrong. So I know that if my path, let's say for instance, so I know the correct output should say something like 0, 7, 8, 6, 5, something, okay? And my best is like 0, 7, 8, I gotta scroll up here and look, 0, 7, 8, 3. That tells me that at some point it considered 0786, and the promising function said no. Aha, here's what I can do. I can add like a big if, saying like if path sub 1 is equal to 7, and path sub 2 is equal to 8, and path sub 3 is equal to 6, I'm going to do some output. What I'm going to output is I'm going to print out the number of vertices in the MST, and I'm going to print out the x and y for all of these. So if this was 4, then I would have 4 sets of x, y coordinates. I would also print out my MST estimate. Now what I can do is I can copy this, paste it into a file, and run it part A. All right, wait, for this to be valid, I've got to make sure that there's no outer decontamination lab area. I've got to make sure that like everything's in the lab or everything's in the outer area, because otherwise my part A should give a different answer. But if I do this, I should be able to see, hey, I got this MST estimate of like, let's say 81.37, and when I run it through part A, it says the actual cost is 52.44. It went wrong. Debug it. How did it go wrong? How did you get these vertices, the right vertices, but the wrong things, the wrong answer? How did it go wrong? You can do some debugging. Another thing, like I said, if you're having wrong answers and you're having trouble visualizing it, look for the link for what's called the visualizer. It's in like the first or second paragraph in the hints and advice section. So go and look at that visualizer and use it. Load up the input and the output, graph it, see what it looks like. Okay, so that's everything for our Project 4 Among Us tutorial video. Good luck on the project, and we'll see you in office hours.